All right, I went a little bit out of order. I wanted to talk about the theoretical yield. What was the theoretical yield?
Theoretical yield is the most amount of possible reaction.
Yeah, the most amount of possible reaction is it. Your book calls it the ideal yield. However, you'll find that theoretical yield is what the term most people use for that. And it's the amount of product formed from the complete conversion of the given amount of reactants to a product. Well, the given amount of reactants, we have to determine, what the, the limiting reagent or the excess reagent determines the theoretical yield. Well, I would have a little different definition for this. I would call the ideal yield or the theoretical yield is the yield predicted from the limiting reagent, limiting reactant. So the theoretical yield or ideal yield is the yield predicted from the limiting reactant, limiting reagent. It's impossible to get the yield predicted from the excess reagent because you just don't have enough. You don't have enough ingredients to make it all. All right, there's two other yields that you have to keep in mind. There's something called the actual yield. And so the way I think about actual yield is, let's say you have enough ingredients. In theory, you have enough ingredients to make 100 cookies. And so there should be nothing stopping you from making 100 cookies. But what happens is, sometimes a little bit of dough is left in the mixing vat. Sometimes there's a little bit of spillage or waste, and so in theory you should have been able to make 100 cookies, but maybe you came up with 99 cookies instead of 100. And that's what we call the actual yield. It depends on who does the cooking, because some people can get better actual yields than others, based on their technique. Maybe they spend more time, maybe some people, they don't have enough time, and so they'll just slop everything together. And so the actual yield is the yield that you actually got. In theory, you should have gotten the theoretical yield, but in actuality, you might not have, because of recovery. A lot of people don't want to scrape every last crystal or every last piece of precipitate out of their test tube. The amount of time it takes to scrape every last piece isn't worth it. You just get most of it and be done. So that's what we call the actual. And so the percentage yield is the actual yield over the theoretical yield times 100%. And so if you manage to scrape every last bit of cookie dough out of there, then you would have gotten 100% yield. But some people don't bother. And so this is important in chemistry because based on our stoichiometry calculations, we predict how much we should have formed, and then when we go to weigh it, actually what we should have formed isn't usually what we get. What we get is something less. And so theoretical yields typically range from the high 90% to even down to the 60% range. In organic chemistry, which deals with hydrocarbons and that type of stuff, combustion is pretty much spot on. It's very close to 100% yield. It's not 100% yield. But there are other reactions due to different factors that yield. Actual yields in the 60% range, much lower, and everything between. All right, so let's take a look at the problem here. All right, a solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Okay, in my problems on the test, I'm not going to tell you what forms. This is like a metathesis reaction. You should be able to figure it out. So on this, I don't like the fact that they tell you what the answer is after we've gone through and learned double replacement reactions and whatnot. And So let's go ahead and figure it out. Barium chloride, what's the formula for that? BaCl2 plus sodium sulfate, Na2SO4. And you know what? They're telling us what the limiting reagent is. How do I know what the limiting reagent is based on the way the question is phrased? Although they don't state it outright. Yeah, excess, that means the excess reagent must be sodium sulfate, therefore the limiting reagent must be barium chloride. So barium chloride is going to dictate the theoretical yield. The theoretical yield is the yield based on the limiting reagent. And so calculate the theoretical yield of barium sulfate. Well, actually this looks like a metathesis or double replacement style reaction. We're going to form barium sulfate. What's the formula for barium sulfate?
ASO4.
Good. ASO4 and what?
Sodium chloride.
Is sodium chloride this, Na2Cl2? Is that the way we'd represent sodium chloride? No. It's just NaCl. We worry about balancing later. In fact, I don't even care about balancing. If there's no driving force, then I don't bother balancing it. But we know that sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So barium sulfate is insoluble, therefore it's going to be a solid precipitate. Since there's a driving force, we need to balance it. So balance by ions, one barium, two chlorides. Well, we need two sodium chlorides here, and it gives us two sodiums there. Then it'd be balanced. All these are aqueous, so I'm going to stop writing aqueous. This would be our conventional equation. We, in addition, have ionic and net ionic, but for stoichiometry, we don't need that. Yeah. And so the yield based on barium chloride. Well, if I have 3.18 grams of barium chloride, then I can just use some stoichiometry to figure out how much barium sulfate that should have yielded. So barium has a mass of 137.33. 133. Then two chlorines would be 70.90. So it gives us 312, 208.23. So here, a mole of barium chloride formula units, this is ionic compound, weighs 208.23 grams. The grams of barium chloride cancel, that gives us moles. And so now we can relate barium chloride to anything else in the equation. And therefore, we'll relate it to barium sulfate. Here it's a 1-to-1 mole ratio. So 1 mole of barium sulfate is formed for every 1 mole of barium chloride that reacts. Gets rid of it. And now I need to figure out the molar mass of barium sulfate so I can do a mole to Gram conversion. And so barium is 137.33. Sulfur is 3207. And 4 oxygens. Okay, 2 oxygens is 32, so 4 oxygens would be 64. So 3 and 7 is 10. That's 4, 9, 13. 233.40. So there are 233.40 grams of barium sulfate in a mole of barium sulfate formula units. Okay, so the moles cancel. So this tells us how many grams of barium sulfate we can expect based on this much barium chloride. So let's go ahead and do that. It's going to be 3.18 divided by 208.23. Times 233.4. 3.56. About 3 sig figs, so I'm going to just carry 1 extra. So we should have gotten 3.564 grams of barium sulfate, did they? You know, that's what they should have gotten, but they lost a little bit, do you see? Because the actual yield is 3.37 grams. And so we could figure out how much they actually recovered, and as far as the percentage goes, that would be the percent yield. The percent yield is given by the actual yield, so-called AY, over the theoretical yield, TY times 100%. So the actual yield is 3.37. Theoretical yield is 3.564 times 100%. Let's see, invert key here. So 3.37 divided by 3.564. I was going to just use the value in my calculator without clearing it. 94.55%. 94.6% was the actual yield or theoretical yield. No, actually, this is not actual yield. This is not theoretical yield. What is this called? Percent yield. And so that means they lost 5.4%. Was lost. How did they lose it? Well, it's easy to lose, actually. It's pretty easy in the laboratory to lose. You don't want to lose too much. It's usually a technique issue, but sometimes it's not. You could have fabulous technique and still.
For the theoretical yield, why did you carry the extra 4 digits if you're only allowed 3 sig big?
Because it's not my final answer. If this were my final answer, I'd stop and round it here to 3 sig big. But this is my final answer.
Are they 2 separate problems though?
They are 2 separate problems, but I need this number for this calculation. So if I were to round it there, I would introduce round-off error, which I don't want to do. Like say, let's say you earn 3.564% interest. And okay, that's your interest, so I'm going to round it to 3.56. Now I'm going to calculate how much money you make. Do you want to round it there, or do you want to round it at the end? So this would be the situation. We still have to do another calculation. If we still have to do another calculation, we call this the intermediate answer. And that's called intermediate round-off. That's a very common mistake, is intermediate round-off in science. So we don't, unfortunately your book is guilty of doing intermediate round-offs as well as many other books are guilty. But in general, we try to avoid intermediate round-offs. Because if you look at the original question is calculate the. Oh, you're right. This is an intermediate answer. Yeah. So they did round it off here, but the second question asked for the percent yield. And so what you could do is, for the answering the first question, 3.56 grams of barium sulfate. But when I do the second calculation, I would carry an extra digit. So when I calculate the percent yield, I would have carried that just one extra digit to help avoid round-off error. So 3.564. It makes a little bit of difference. If you look at my calculation netted 94.6%, whereas their calculation netted 94.7%. Which one's more accurate? The 0.6%. So if you're paying interest, then mine would benefit. If you're receiving, theirs would benefit. Okay, this is doing it in the reverse direction. In the reverse direction, we use percent yield as conversion factor. And so they're saying solid sodium nitrate decomposes to solid sodium nitrite and oxygen gas upon heating. So let's first do this one. This one, okay, solid sodium nitrite. So what's the formula for sodium nitrite?
It's nitrate.
Okay, solid sodium nitrate. What's the formula for solid sodium nitrate? NaNO3. And then what they're doing is they're heating this. Heat. Okay, and so when we heat things up, eventually they're going to break down or decompose. When we think about breaking these things down, they could break down into the elements, like sodium, metal. Well, it depends on how hot. Sodium melts at a pretty low temperature. Nitrogen and oxygen. But this is an example of what type of a reaction, Is it a metathesis reaction, heating this? Acid base? This is an example of a redox reaction. And redox reactions like this, you just heat it and see what happens. We heat it and see what happens. So at this particular temperature, this is what happens. It decomposes into sodium nitrite, which is what? NaNO2 and O2. Under other conditions of temperature and pressure, it could decompose into other stuff. And so typically when something like this decomposes, it might decompose all the way to the elements or it might decompose into other compounds like this. But this is a redox reaction here. So redox reactions can be tricky to predict. That's why we have the skeleton. Do you predict the products in the skeleton redox? No. We just try it and see what happens. Well, we try this and see what happens. This is what happens. Is it balanced? Okay, normally when we balance this, we split it up into half reactions, etc. But this is not a skeleton. I can tell this is not a skeleton because they're just telling us what forms from this. So they're telling us all the products. And so in this case, we're just going to balance it as is. So I have one sodium, one nitrogen, 3 oxygens, 4 oxygens. So how can I balance it? Okay, now it's balanced. Okay. All right. And so this reaction typically has a 95% yield. And so a 95% yield is typical. And so what we're going to do is we're just going to use that. Since most people are getting 95%, let's go ahead and factor that in to the stoichiometry. And so let's factor this in. Alright, so what mass of sodium nitrite will be produced by the decomposition of 1.50 grams of sodium nitrate? Oftentimes we do this. We factor in the percent yield. Like say, for example, you need 100 cookies for a big event. Then you probably want to make extra, a few extra, or plan to make a few extra. Maybe you should plan to make 103 in case 3 get broken or whatever else happens. And so this is the type of stuff. If we know we're going to lose a little bit, then we better make a little extra to compensate for the loss. Right? And so that's one way of doing it. Another way of doing it is, well, let's just factor in the loss. You know, if I'm planning to bake 100 cookies, how much do I expect to have at the end? And so that would be like this type of problem here. You know, if I plan to make this much, well, and I have a 95% yield, then let's factor that in and see how much we can expect. And so what mass of sodium nitrite will be produced by the decomposition of 1.50 grams of sodium nitrate? So 1.50 grams of sodium nitrate is where we start. And so what we can do is we can figure out what the theoretical yield is, right? So 1.50 grams of sodium nitrate, and let's go ahead and get the molar mass of that. Sodium is 2299. Nitrogen is 1401. 3 oxygens would be 4800. It's 10, 15, 8500. And so a mole of sodium nitrate formula units weighs 85.00 grams. Here, of course, we don't have to worry about limiting reactant and excess reactant because there's only one reactant, sodium nitrate. And so grams of sodium nitrate cancel, that leaves us moles of sodium nitrate. So for every 2 moles of sodium nitrate, we should get 2 moles of sodium nitrite. So it's a 2-to-2 ratio. So 2 moles of sodium nitrite for every 2 moles of sodium nitrate. Or it's, you should do 1-to-1. The 2. All right, up to this point, what we have is, actually, let's go one more step farther. And so sodium nitrite, let's figure out the molar mass of that. Sodium is 2299, nitrogen is 1401, and now we have 2 oxygens. 2 oxygens, 3200. What do you get?
69.
69? So there's 69.00 grams of sodium nitrite per mole of formula units, or per mole of sodium nitrate. Pretty soon we drop that formula unit just per mole. And so everything works out. Moles sodium nitrite goes to grams of sodium nitrate. Okay, this is, if we stop here, what is this called? If we stop here, this is called the theoretical yield of sodium nitrite. That's how much, in theory, we should be able to get, but you know, sometimes it's hard to get all of that. Instead, we got to anticipate we're going to lose how much? We got to anticipate we're going to lose about 5%. Right? Because it only has 95% yield. And so this is how we do it. A 95% yield means this. Well, it means 95 grams of actual yield over 100 grams of theoretical yield. It's 95% yield. So for every 100 grams of that I predict I'm going to make theoretically, I'm only going to get 95 out of that. So this will be we're going to factor this in here. So let's go ahead and do the calculation. 1.5 divided by 85 times 69 times 95 divided by 100. So in actuality, we're going to expect 1.156 grams of sodium nitrite. The actual. It's compensating for a 5% loss. Let's see how to put this. Okay, here they did it the same way. They got the theoretical yield and they converted it to actual yield. That's what we got. That's what we did. We got the balanced chemical equation and then did this here. Making that 95 grams. Oh, you know what? I got the sig figs wrong. Here. They're correct. I'm only allowed 2 sig figs because this is 2 sig figs here. So I'm going to round to 1.2 grams. All right, so that's theoretical, actual, and percent yield. And then we talked about limiting reactants. We talked about that before. Okay, the next thing I need to talk about is energy. Here, energy. Energy is expressed in different units, such as the joule. The joule is what we call the SI unit of energy. It's shown here, SI. You know what SI stands for? The International System of Units. This is the internationally agreed upon standard for energy, which is the joule. The joule is like this. It's the amount of energy required to lift a 1 kilogram mass by 1 meter. That's the joule. And so this is why it's a kilogram, and then one of these meters belongs to lifting 1 kilogram mass by meter. The other is meters per second squared. Have you ever heard of a meters per second squared? There's something very famous, 9.8 meters per second squared. You heard that? That's called gravity. It's the gravitational force. It's lifting a 1 kilogram mass up 1 meter against gravity. You know, lifting it up, it's going to cost you some energy. Well, how much energy does it cost? Well, it's going to cost you 1 joule. So think about 2.2 pounds, lifting it up 3 feet. You've just probably used more than 1 joule worth of energy. That's loss, you know, and inefficiencies there. But the joule is that. We also have the calorie. There are 2 types of calories. There's the calorie with the small c, like this, CAL. And then there's a calorie with the large c. The small c calories, the energy required to raise the temperature of 1 gram of water by 1 degree C. So if we want to heat up water, a gram of water, we want to heat it up by 1 degree C, it's going to cost you 1 calorie. That's how it's defined, actually. Well, if you want to do the same thing in joules, it's going to cost you 4.184 joules to do the same thing. 4.184. And so heating up 1 gram of water either costs you 1 calorie or 4.184 joules. Therefore, this is a conversion factor between joules and calories. There are 4.184 joules for every calorie. So joule is quite a bit smaller, you know. There are about 4 joules in a calorie. Calories can get bigger quantity of energy. In chemistry, both of those are still kind of small because we usually heat a lot more than 1 gram. And so we use kilojoules and kilocalories.
Does this calorie that I can deal with that you eat, like how many calories?
Yeah, it does. And that's the last one here. A food calorie. A food calorie, you know, like say you just ate a 2,000 calorie meal. Well, actually you didn't. You ate a 2 million calorie meal. But who wants to think about eating 2 million calories worth, right, of food? And so what they do is a food calorie is 1,000 chemical calories. So there are 1,000 chemical calories in a food calorie. So let's say you have a beverage. You know, it's a low calorie beverage is 1 calorie. Well, it's not really 1 calorie. It's 1,000 calories. It depends on how closely you want to look at it. I was reading this thing on the soda machine. Where was it at? Maybe it was at across the street here, and it said, according to FDA rules on rounding, these drinks have 0 calories. But those are food calories. Obviously, they don't have 0 calories. They got some calories. But it depends on how precisely you want to look at it. So a lot of reactions yield energy. So this is just a standard conversion. You know, calculate the number of kilocalories, calories, and joules in 42.5 kilojoules. 42,500 joules is what that is. So let's just look at this here. So we're given 42.5 kJs. kJs would be kilojoules. We want that. So this is just dimensional analysis. I probably wouldn't have. Here's some conversion factors. So 1 kilocal. Your book does this. I just, I don't like this. I just do 1 calorie is equal to 4.184 joules. I mean, you could do this if you'd like to do that, but I don't. I just like to memorize one. That's it. And so I would have done this problem differently. This is the way I would have done this one. On the one hand, you might think, oh, great, the more variety you see, the better. But this isn't really variety in the sense that you're going to get a wide breadth of problem-solving ability. This type of variety is not necessary. You want other types of variety that will show you alternative strategies to solve it. So I have 42.5 kilojoules. So I want the first thing I do is they want joules. So what I do is this. If they want joules, there are 1,000 joules for every kilojoule. And so this is going to give me 42,500 joules. That would be it. Or 4.25 times 10 to the 4th joules. If you want to guess the card numbers. Or 42.5 times 10 to the 3rd joules. This is exact, of course, kilojoule, joule. And then I could go to calories next. To figure out the calories, I'd do 42.5 kilojoules, and then convert that to joules, 1,000 joules per kilojoule, and then go to calories. 1 calorie with a small c is 4.184 joules. So kilojoules cancel, joules cancel, that gives me the calories. How many calories is that? Let's calculate that. 42.5 times 1,000 divided by 4.184. I get 10,157.7 calories. So we could round this to 10,200 calories. That would be 3 sig figs for 10.2 times 10 to the 3rd calories. 10 to the 3rd is 1,000. so we could replace 10 to the third with K kilocalories, or we could just do another problem. We set it up as another problem here. Setting it up as another problem, I'd take 42.5 kilojoules, convert it into joules. The reason I do this is because I just want to remember, I don't want to get confused with the units ever, I just want to remember that 1 calorie is 4.184 joules. I don't want to remember kilojoules or kilocalories or whatever else, or millijoules. You know, your book would do millijoules and millicalories. I don't want to do that. I just want this as the center here. But then we're going to kilocalories, so that means there's 1,000 calories in a kilocalorie. So this would give us 10.15 K counts, which is equal to 10.2 K count. All right, so those are some unit conversions. All those are equal amounts of energy there. The next thing we're going to look at are thermochemical equations. And so one way of knowing that there's energy involved is if the temperature changes. You know, you guys remember kinetic molecular theory? Temperature is a measure of what, based in kinetic molecular theory? The higher the temperature, what do you visualize? The higher the temperature, the more collisions, more motion, etc. The higher the temperature, in other words, the higher the energy. So heat given off or absorbed in a chemical reaction can be measured in the laboratory. The change is called heat of reaction, or enthalpy of reaction. Enthalpy is a thermodynamics talks about, you know, the energy. And enthalpy is a word, you know, you could call it energy of reaction, but there are different subcategories of energy and how we look at energy. And one of them is called enthalpy. Enthalpy is often exchanged as heat of reaction, enthalpy of reaction, but there are other heats too. In addition to enthalpy, we have something called internal energy. But those details we don't talk about in Chem 4. Those details we'll talk about in Chem 1A. So don't worry about this word. I don't even know the origin of enthalpy, you know, where it came from. I just know the definition. Enthalpy this is not the best here. They're saying heat content of a chemical system. When people think about heat, they think about motion, you know, thermal motion. And so this is misleading, because in chapter 1 we learned about 2 types of energy. What are the 2 types of energy? We have energy of motion, and we call that what? Kinetic energy and potential energy. And so when we're thinking about the heat content, we're just thinking about the motion, right? But that's wrong, because and I can understand why they want to do this. They want to do this because they don't want to. Well, I don't know. I don't understand what they're doing, because, you know, if they're going to bring up kinetic and potential energy in chapter 1, I'm surprised they talk about it like this, because now they're totally ignoring potential energy. And so it's not heat content, it's not the motion, it's this. And so if we look at the heat content of, let's look at water at 25 degrees C versus nitroglycerin at 25 degrees C. Some people might be misled into thinking that both of these are at the same temperature. So they're at the same temperature. They both kind of have the same motion, the average motion. They move differently. They'll have the same average motion. And therefore they'll think they have the same heat content, but they don't. They have totally different energies. Why do they have totally different energies? Back there. Just go straight. Are we on break?
You're going to break it at 11:30.
Oh, that clock is wrong. Yeah, pretty soon.
Okay. Can I talk to you?
Yeah.
Is it because the molecules are different sizes?
Sorry?
Is it because the molecules are different sizes?
Nitroglycerin is a higher.
Well, they move differently, but they have the same average kinetic energy. It's like you could have a little car and a big car have the same average kinetic energy, but the little car's got to be moving a heck of a lot faster, And so that's it. These atoms weigh different amounts. So you have light atoms and heavy atoms, and they have the same average kinetic energy. Some got to be moving faster, some got to be moving slower. And so both of these have the same kind of heat content, but not really. Because we aren't looking at heat. Heat, normally when we think about hot objects or cold objects, we're thinking about motion, right? And so these have the same kind of thermal energy, but what's different is their potential energy. Nitroglycerin has the potential to explode, whereas does water have the potential to explode? No, and so nitroglycerin has a much higher energy. And so what they're saying is that nitroglycerin has a much higher heat content, but does it really have a higher heat? And so it's misleading. This is not the jargon that's used, And so they're trying to make it simple, but they're making it more complex, unfortunately. And so the enthalpy is not just the enthalpy is this. It's kind of the well, anyway. So I'll just leave it at that. I'm not going to get into it because this takes too much time. So H is the symbol. So when we see H, that stands for enthalpy. Delta indicates a change. And so oftentimes we say delta H. Do you know what this little r means here? Reaction. So this is delta H for a reaction. If it has a negative value, we say that the reaction is losing energy. If it has a positive value, we say the reaction is gaining energy. But is there such thing as negative energy? Yeah, I mean in a conceptual sense, but in a physical sense, is there such thing as negative energy? So for example,
Yeah, there's antimatter. That's technically negative.
all right. Aside from that, let's say, aside from that, what I'm asking is there such thing as a negative $10 bill? Can you give me a negative $10 bill? I'd like you to give me a negative $10 bill, and then you probably want to give me a negative $10 bill because then you can because a negative $10 bill means I must have lost $10, right? That's what it means. But did you lose a negative $10 bill? If you have negative $10, does that mean you had a negative $10 bill that you lost? Or does that mean you lost $10? That means you lost $10, positive $10. This is the same thing. If somebody says negative 100 kilojoules. Give me negative 100 kilojoules. You'd say, what the heck are you talking about? There's no such thing as negative 100 kilojoules, right? The negative is just for bookkeeping. The negative is for bookkeeping, you know, to do pluses and minuses. Debit your account or credit your account. That's all. But there's actually no such thing as negative 100 calories or negative 100 joules. But anyway, we give those reactions. If a reaction loses energy, we call it exothermic. Exo means, you know, outside. Thermic. Exothermic. If a reaction gains energy, we call it endo. It's going inside. Thermal. Endothermic. For exothermic, it's a loss, so we treat it as negative. For endothermic, it's a gain, so we treat it as positive. Now, there's something called the first law of thermodynamics. The first law of thermodynamics you've already heard. The first law of thermodynamics says that energy can neither be created nor destroyed. We heard that in chapter 1. And so if somebody loses $10, somebody else must have gained $10. All right, so there are two ways of expressing energies involved in chemical reactions. So for example, if we combust ethane, we saw this earlier. If we combust ethane, we're going to generate a lot of heat. Well, how much heat are we going to generate? Well, combustion of 2 moles of ethane here will release 2,855 kilojoules of heat. And so the way I read this is that I'm going to get 2,855 kilojoules for every 2 moles of ethane that completely combusts, in theory. The other way of doing that is, since I'm losing this, it's a product. And so one of the products of combustion is energy. And so I could just add it. So this would be a stoichiometric factor that we can factor in. And so we can come up with a whole bunch of stoichiometric conversion factors. 2,855 kilojoules per 2 moles, per 7 moles, per 4 moles, per 6 moles, as the reaction is combusted. If we heat up ammonia, this is another reaction. This is a redox reaction here. If we heat up ammonia, it's going to cost us energy. And so in this particular case, it's consuming energy, 92 kilojoules worth of energy for every 2 moles of ammonia to react. If I had 4 moles, it'd be double that. If I had 6 moles, it'd be triple that. And so for 2 moles, it's 92. For 1 mole, it's half that. Or I could write it like this. Delta H for this reaction is equal to plus 92. Plus 92 means it's got to consume it. Negative means it's going to release it. So we put it there. Energy is always positive, so when we write in the equation, it's always positive. Negative and the positive just tell us what side of the equation it's on. This is, you know, I was, what was it? Actually, I was, over the summer I was watching some documentary about concrete and the Romans, you know, how Romans developed concrete and revolutionized construction, architecture, everything else. And it was interesting because the historian, this guy was saying that, you know, because of a stable food supply, that the Romans were able to experiment, do a lot of experiments. And one of the experiments they were able to do was, and also they had coal or something like that, so they could get high temperatures. One of the experiments that they did was to heat up limestone to very high temperatures. When they heat up limestone to very high temperatures, they were able to make lime, calcium oxide, which is called lime. Lime is a key ingredient in concrete. So it's pretty interesting. It was about chemistry. formed this thing. So anyway, let's take a look at this, the thermal decomposition of limestone. It costs a lot of energy, and so they had to have a good energy source. Well, one good energy source is coal to get very high temperatures that were required for this particular reaction to go. So here we have calcium carbonate, solid. The symbol for heat is this delta 2. And so delta is used for two things. One, to indicate a change, and two, to indicate heat. And so if it's written under the arrow like that, it just means we have to heat this up. Oftentimes we put the temperature that it goes at here, because there's going to be some temperature. And then we form calcium oxide and what else? Plus CO2. Now, when we look at this decomposition reaction is different than the last decomposition reaction. Because the last decomposition reaction we looked at was a redox. You know, it was the sodium nitrate going to sodium nitrite plus oxygen. That was a redox. This one is not. This one, how do I know it's not redox? By looking at it, I might be tempted to say it's redox. But by looking at this more carefully, it's not redox. How do I know? How do I know this is not redox?
Is it because
Okay, one of the requirements is in redox, the oxidation states must change. In acid-base reactions and in metathesis, the oxidation states never change. They always stay the same. And so when we look at this, calcium is 2+, oxygen is 2-. That means carbon is +4. Calcium is 2+, oxygen is 2-. Oxygen is 2-, carbon is +4. And so none of the oxidation states have changed. So this cannot be redox. And so we eliminate redox. Is this metathesis? This is not metathesis either. Is this Bronsted acid base? This is not Bronsted acid base. Do you know what this is? Well, if it's not metathesis, it's not redox, it's not Bronsted acid base.
it's a decomposition.
It is a decomposition, but what? Decomposition, redox? Decomposition, what type of decomposition is it? We want to know because we want to understand patterns. And if we don't see any kind of pattern, then we aren't going to be able to understand reactions very well. Was there one other? Was there 4?